Let's look at some examples. Find the gradient of the following scalar fields. So A, the scalar field phi equals 1. This is a constant field, and therefore the gradient of phi is the partial derivative of phi with respect to x, partial of phi with respect to y, and partial of phi with respect to z. So the answer is obviously the vector 0, 0, 0. The gradient is 0 everywhere because this scalar field is constant everywhere. So therefore there is no direction of steepest ascent and there is no change in the scalar value. To illustrate this, I can go to this Mathematica applet where I was showing the example I showed you in the last video, but I can actually change my function, so I can make it a constant function. So now the function is equal to 1, so you see that the height of this scalar field is constant, and therefore the gradient everywhere is 0. There is no direction of steepest ascent. Okay? Great. Let's do B. So the scalar field in B is x plus y plus z, which means that the gradient of phi is equal to the derivative of phi with respect to x, the derivative of phi with respect to y, and the derivative of phi with respect to z. So if we calculate that, our answer is 1 plus 0 plus 0. That will be the derivative with respect to x. Sorry for interruption. So yeah, derivative of phi with respect to x, that's 1 plus 0 plus 0. Derivative of phi with respect to y, that's 0 plus 1 plus 0. And derivative of phi with respect to z, 0 plus 0 plus 1. So our vector, the gradient is 1, 1, 1. Okay? So it is a vector field that is constant everywhere. So let's have a look at that in our applet. If I change the function to the function x plus y, here we are in 2 dimensions, so I cannot do x plus y plus z. I'm only doing a 2-dimensional scalar function, x plus y. So this corresponds to a plane, to a flat plane in 3 dimensions, okay? So now the gradient, which is this red arrow, is just a vector in the direction 1, 1. So x hat plus y hat. So the red arrow is constant. It's the same everywhere, because the direction of steepest ascent is constant everywhere, and the length of the gradient, the slope of this ascent is the same everywhere. So the length of the arrow is the same everywhere. Okay? Finally, one last example, the exponential of minus x times y times z. Okay? So if we calculate the gradient of this, the gradient of this is equal to derivative of phi with respect to x, derivative of phi with respect to y, derivative of phi with respect to z. So what's the derivative of this exponential with respect to x? So it will be the derivative of the exponent with respect to x, which is minus yz, times the exponential again. Then the next will be the derivative of the exponent with respect to y, which is minus xz times the exponential. And finally, we will get minus xy times the exponential. Okay, remember your partial derivatives. So this is clearly a more complex function. So now this is really a vector field which depends on position. Okay, so now in the Mathematica applet, I'm going to do a slightly different one, a 2-dimensional one. So I'm going to plot this scalar field and its gradient, which is equal to minus y exponential of minus xy and minus x exponential of minus xy. So I'm going to plot how this looks. This is a very simple operation, and yet it looks amazing. So if I change the function to the exponential of minus x times y, you get this absolutely amazing shape, which is equal to 1 at the origin. So this is the origin of x and z, and then it grows greatly in this direction and also in the other direction. Yeah. But you can see how the arrows, which are this gradient, which are this expression we found, clearly tell us the direction of steepest ascent, and also they get really big near this really steep side walls of the mountain. Okay? And that's all contained in this beautiful mathematical equation. So these are the red arrows, while this was the yellow surface. Okay? So the scalar field was the height, and the arrows were the gradient. Great. So I'm confident that you now can calculate the gradient for any field I give you, and you also know how to interpret it. Thanks for watching. See you in the next video.